Welcome to our channel for R programming. In this video, we will show how to use t-distribution and t-test in R. So we know t-distribution is a bell-shaped, or say the symmetric density distribution, and it is actually comes from the random variable from standard normal distribution divided by a random variable of chi-square distribution divided by its degrees of freedom. So here say is a standard normal distribution random variable, and V is a chi-squared random variable. Then this small v is the degrees of freedom of this chi-square random variable. So the square root in denominator, then this term called t has followed t distribution with v degrees of freedom, and its density function quite complicated. Here is a gamma function, and the t distribution's possible value from negative infinite to positive infinite. It is quite close to normal distribution. If we look at these figures, so several curves for t-distribution in terms of its degrees of freedom. So you can see if the degrees of freedom becomes larger, very large, then t-distribution is the same as a normal distribution. So this is the largest degrees of freedom. So usually t-distribution has longer, wider tail than normal distribution. So t-distribution is often used in a small random sample to estimate or do hypothesis testing for the population mean. So say x1, x2, xn are random variables from a normal distribution with mu in the mean and standard deviation sigma. So if we let the sample mean x bar equals n 1 divided n times sigma xi from 1 to n, then this is the sample standard deviation. So the sigma xi minus x bar square then divided by n minus 1, because when we lost 1 degrees of freedom in calculating the sample average, so we use n minus 1 in the denominator. Then this random variable x bar minus the population mean divided by sample standard deviation divided by the square root of n has a t distribution with n minus 1 degrees of freedom. So t distribution's density function look like this. So this value usually called critical value, t alpha, used in the t-test. So this alpha, for example, we set 0.05 for one-tailed test. So if for the two-tailed test, here alpha, here is half alpha here also. So this blue shaded area in this curve represents, for example, 0.05 for the type 1 error. So significant level also say. So in the test, if we get a test statistic in the right side of t alpha, or we get a p-value less than alpha, so we say the test is significant at the level of alpha. So next we will show how to use t-distribution in R programming. So usually in R programming for odd distribution, we use the form dpqr. So one of these 4 alphabets, then plus the abbreviation of this distribution. So for example, for t distribution, we just have t, dt, pt, qt, and rt. So these 4 alphabets represent a density and a cumulative probability, quantile value, and a random number generation. So next we show how to use these functions and how to do t-test in RStudio. So the first function is dt. It is used to calculate the probability density for the random variable coming from a t-distribution. So say we create a random variable vector from 0 to 10 with the gap 0.2, and we set a degrees of freedom 10. Then we can use dt to calculate all distribution density for this random variable vector. Then we plot in a figure. So this is the density curve for these 10 variables coming from a t-distribution with 10 degrees of freedom. The second function is pt. It is used to calculate the cumulative probability for random variable, so up to this random variable. So we also create a vector for the random variable 0 to 10 and degrees of freedom 10. We can use pt x is a vector, random variable vector, and with degrees of freedom. We plot in a figure. So this curve can see between 0 to 2, the cumulative probability increase very deep, and after 2 it's quite flat, almost no increasing, almost close to 1, for example 3. So which means in this part the density very big. The larger density will means the derivative of the cumulative probability, right? Cumulative probability actually is the integral of a density function. So here quite deep and here quite flat. And the function qt is the opposite operation of function pt, so which is used to calculate the quantile value from the given cumulative probability. So here we have to set a cumulative probability vector between 0 to 1. Then say we set degrees of freedom 5. Then you can use qt to calculate all the random variables from given cumulative probability. So we show this curve. So this is the quantile value. Quantile value actually is a random variable number. So for example 0.4, which means the cumulative probability 0.4 about minus 0.2, this value, which means about 40% of the variables in this t-distribution has the value less than minus 0.2, right? And the last function is rt, which is used to calculate or generate a random number. So we set n equals 10,000 and degrees of freedom 10. Then we use rt to generate 10,000 random numbers from this t-distribution with degrees of freedom 10. Then plot in a histogram. So this histogram shows the counts for each value beings from this random number, 10,000 random number. So quite close to a density for a t-distribution with 10 degrees of freedom. So then we show an example of using t-test. So the problem is a chemical engineer claims that the population mean yield of a certain batch process is 500 grams per milliliter of raw material. To check this claim, he samples 25 batches each month. If the computed t-value falls between minus t0.05 and t0.05, he is satisfied with this claim. So what conclusion should he draw from a sample that has a mean x bar equals 518 grams per milliliter and a sample standard deviation s equals 40 grams? assume the distribution of Yas to be approximately normal. So the population is approximately normal, and we get a random sample of size 25. So 25 is a small sample, less than 30. So we can use t-distribution to test if the random sample comes from this population, right? So first we create the t-critical value. So t-critical value, if we look at here, we will calculate this value, t-critical value. And the t-critical value here, because alpha is 0.05 for both ends, right? Because alpha minus also t 0.05. So this is a two-tailed test. And actually, if we look at a big alpha, it's about 0.1 because we have to add these two. So this is half alpha, 0.05. Then we calculate this critical value, use Qt. Qt is because this is 0.05, which means the white area is 0.95. And Qt for calculating the quantile value of this cumulative probability under 24 degrees of freedom of a t-distribution. Then we calculate and get 1.71 for this critical value. Next, we can use the sample to calculate the t-statistic from the sample. Sample is x bar minus the population mean. We have to test this the mu divided by the standard deviation of the sample, then divided by the square root of the sample size, right? So we get a t-sample with 2.25. Now we can also calculate the p-value of this critical value. So critical value we got. Then we get the p-value. We have to calculate the critical value stay here, right? We have to calculate the blue area and the right side of this critical this t-statistic. So this 2.25, and the critical value is 1.71. So we get p-value is 0.0169. So the conclusion is, because t-sample larger than t-critical value, because we get a 2.25 larger than 1.71, right? So also we say p-value is less than 0.05, right? We get a critical value larger than this. We get the t-statistic larger than this critical value, and we get the p-value also less than this alpha, right? So the conclusion is that we conclude that the process produces a better product than he thought. So, which means from this sample, we conclude not to come from this population, because we get the very large t-statistic and very small p-value, very unlikely occurred event now occurred. So this is unlikely that this random sample come from this population in hypothesis 0, in the H0 hypothesis, right? Thanks for watching.